Alright, so to determine our Z score, we need to use our calculators. It's just that simple. So with assess normality, we know that we can assume normality. In the second one, we're trying to find the confidence interval where we've got 99% confidence about the reading times, the portion people who regularly read. So the first thing we need to do is to find our Z score. How do we do that? Must be done on a calculator. Inverse normal. What do we set the area to be? 0.99. If I set it to 0.99, I've got to make it what? Central. So if I do that, I'll get 2 scores, and what do I have to change my standard deviation and my mean to?
0 and 1.
Yeah, 0 and 1 or 1 and 0, you know which one goes where. Do I have to do 99%?
Yeah.
Could I put another area in? Point, not 01? Not 0.01? Although O is not a number. 0.005, and I can set a left or a right tail. Sweet. Why do I set it as 0.005, not 0.01? Only half, yeah. Either way, when I do that, I get a Z score of 2.575. Try and keep as many decimal places as we can. 3 is probably enough. So now I know my Z score. I need to determine my confidence interval. Now, the confidence interval formula we'll all recall is equal to p hat, which is just the mean, the value we're expecting, plus or minus the square root of p hat, 1 minus p hat over n, and that should all be multiplied by z. What do we call the thing on the right that we're plussing and minusing? The margin of error. I now sub in my values. So I get not 650, that's good, my 8's at what 5 anyway. 1685 plus or minus 2.575 times the square root of 650 and I shove that in my calculator. Do I need to represent those as fractions? No, I can do them as decimals. The reason I do them as fractions is because that sometimes, very rarely, but sometimes these do come up on tech-free exams, and we need to be able to do them with both calculator and non-calculator. If I was doing non-calculator, I would strongly recommend keeping them in fractions. Yes. You were saying it?
How do you work out those rules?
Like it would be like a 95 percentile.
Oh, yeah.
And the P would be like 1 on 4, and then 3 on 4 would be the other one. And then your M would be some number that you can deal with. Like it'll end up being a number you can square root. Rare, it doesn't come up often. It's not the kind of content I would usually assess, but it does come up. So if I show you fractions and you do it like that, it works for both.
And you want hats for the exam?
Yeah.
Like,
Not going to mark again probably for that, but yeah. It is a sample proportion, not a population proportion here.
Yeah.
Yeah. Cool. What do we got? Confidence interval. It should be 2 numbers.
Do you have to put that in a certain one?
To do what?
Just like the normal.
Yeah, just the normal run matrix. Yeah. We got a value for us? Surely we got a value.
Yeah.
Lower, what's the lower value?
0.304.
So 35.5% to?
30.41.
Very good. Sounds pretty good to me. Which means that the statement about what do you think of do the results support the conclusion that less than half the population regularly read based in regular read, which is what we're trying to assess, correct or not?
Yes.
That is correct. And we are more than 99% confident that that's the case, because it's it's above our range, outside of our range of our confidence interval. Clear? So for D, the reason I asked this question is because it's pretty much got all the key types of questions that we ask frequently with these types of problems. So we've got a confidence interval question, we've got a normality assessment, we've asked to talk about it, and then in question D, it's saying what do we need to do to create, or how many people do we need to create a 1.5 margin of error in a 99% confidence interval. So what's my margin of error equation? Because I always should start with writing down what I know. Z square root P hat over N. Do I know P hat?
Yeah.
0.39, which means that my margin of error, I know my Z score, what's my Z going to equal? It's a 99% confidence interval.
0.33.
What's that?
Huh?
2.575, yes. And our margin of error? Do we know margin of error?
Yeah, 0.015.
Make sure we put it in decimal form, not in percentage form. Cool. So then I just sum in what I know, and I've got one unknown there. So 0.015 is equal to 2.575 multiplied by the square root of 0.39 by 0.61 divided by n. What do I do with that? Yeah, we'll rearrange. We shouldn't have to rearrange, but just in case we don't. Go through that. What does that equal? 0.015 divided by 2.575 squared. Someone want to tell me what that is? The left hand side, 0.015 divided by 2.5.
3.39 times 10 to the negative 5.
We are going to do a lot of scientific notation because we have very, very small numbers. Shove that in, and we should get our sample size. Now, are we expecting it to be bigger or smaller than our previous sample size? Bigger, very good. And what do we get?
7,000.
7,010. Should we have a decimal amount of people? If I had 7,009.2, what would my answer be? 7,010, because I've got to round up to get over that value. Does that make sense?
Why so much?
Because you need a big sample. We had 1,600 people to get a margin of error of about 3% before, 2% before. So we started at 0.39. That was 2.5%. Did you use brackets around the bottom? Okay, I'll check that. Rightio, are we all good? We can now, I wouldn't mind just having another crack at one of those actually, just based on how we went there. I want us to do 15 and I want us to do 17. 15 and 17. So 10.4 15 won't take very long, 17 will take a bit longer.